Now there's one thing that actually turns out to be fairly neat, although you might not fully appreciate it. This expression, square root of x plus h minus square root of x over h, can be, in a sense, rationalized in a way that's very useful. It's kind of the reverse of the way you usually see things rationalized, but let's do this. 6 times the square root of x plus h minus the square root of x over h is equal to 6 times the square root of x plus h minus the square root of x over h multiplied by the square root of x plus h plus square root of x over square root of x plus h plus the square root of x. In other words, all I've done is I've multiplied numerator and denominator of this by the square root of x plus h plus the square root of x. The advantage of that is that what I get is 6 times, okay, if I distribute this multiplication of the numerators, I get square root of x plus h times the square root of x plus h, which is just x plus h. Then I get minus the square root of x times the square root of x plus h. Then when I continue the distribution, the square root of x times the square root of x plus h is plus that square root, which is this equal and opposite to what I get when I multiply these two terms. And then I've got another square root of x times square root of x. So I get x plus h minus x in the numerator. In the denominator, I get h times square root of x plus h minus the square root of x. Should be clear that the x's subtract off, leaving me just h in the numerator. H in the numerator is divided by the h as a factor of the denominator, leaving me just 1 in the numerator. So I get 6 times 1 divided by and that should have been a plus square root of x plus h plus the square root of x. And the parenthesis needs to close the whole thing. Okay? And that's a very useful simplification because, as I said earlier, we think about what happens when we shrink this interval to 0, when h approaches 0. If h approaches 0, what happens to this denominator? Well, h approaches 0, so the square root of x plus h approaches square root of x. So our denominator approaches square root of x plus the square root of x, which is just 2 times the square root of x. So let's come up here. 6 times 1 over the square root of x plus h plus the square root of x approaches, as h goes to 0, as h shrinks down to 0, approaches 6 times 1 over the square root of x plus the square root of x, which equals 6 times 1 over 2 square root of x, which equals 3 over the square root of x. And we could rationalize that as 3 square root of x over x, but we'll leave it in this form. Now remember that this expression represents an average slope of this graph. As h approaches 0, that average slope approaches the slope of the graph at this point. In fact, the slope of the tangent line at this point. So we draw a line that's tangent to the curve at this point. it will have exactly this slope. So this is slope of the tangent line at x f of x, at the point x f of x. And in general, if you have a square root of x, the 6 is just along for the ride. If the 6 wasn't there, you would have the same expression for the square root of x plus 7. And there are things there we don't need to worry about. But that comes out 1 over 2 times the square root of x. And it wouldn't matter if this was plus 48,000. Remember, the 7 subtracted off when we did this previously. If you do it correctly by grouping the f of x in the original expression, whatever that number is, if it's a constant number, it's going to subtract off. If it doesn't depend on x, it's going to disappear. So what we've derived is an expression for the slope of the tangent line to the square root of x. If we've stretched that function by a factor of 6, then it's going to be 6 times that. The slope will increase along with the stretch. Now, there's a lot in what I've said that you don't need right now, and you don't need for this course, but it would be to your advantage to at least let the neurons run over that idea a little bit. And if you understand it well, that's even better, because it'll make it much easier. If you understand it, it means that you are a good candidate for an applied calculus or calculus course. If you don't understand it, that doesn't mean that you aren't. But if you do understand it, it means that you are a good candidate for those courses. And you should have a fairly easy time, and it won't hurt you to, it'll actually help you significantly to get used to these ideas in the process of thinking about the things that you need to do well in the test for this course.